So, good day guys. Welcome again to C009 Mechanics of Deformable Bodies. So, just to recap what we have studied on our previous discussion, previously we studied about how uh, how to get the internal forces acting inside a beam using the method that we have discussed before, which is the method of sections. So what does the method of sections tell us? So the method states that if we have a beam loaded by some type of loadings, for example, we want to find the internal forces acting at a specific location inside a beam, say for example, this location, all we have to do is cut the beam into segments. So there will be left segment and right segment. And since we have disconnected these two segments of the beam, we know for a fact that there will be internal forces that will come out on the disconnected part of the beam. And since we assume that the connection of the beam to itself is rigid or fixed connection, we know for a fact that the internal forces that will come out will be a horizontal force, a vertical force, and a bending moment. So we usually call the horizontal component of that internal force the normal force. And the vertical component, we usually call it the shear force. And the moment component of that internal force that will be exposed when you disconnect this beam is what we call the bending moment. And take note that the magnitudes of these internal forces are equal but opposite in direction. So what does method of sections tell us? It states that if the original structure, the beam, is in equilibrium, therefore the its segments must be in equilibrium as well. So meaning, for example, if we will look at this left segment, uh, method of sections tell us that this segment must be in equilibrium as well. Meaning, if we sum up the summation of forces along the horizontal direction, along the vertical direction, and as well as the moment at any point on this left segment, they must be all equal to 0. And as well as on the other segment. So if we sum up the forces along the horizontal, vertical, and moment at this right segment, the summation must be 0 as well according to method of sections. So this is how we can get the internal forces acting inside a beam that is loaded by some type of loads. So we can use this method if we want to, according to what we have discussed before. Or we can use the formula that we have formulated on our previous discussion, which tell us that the shear force, which is this, acting on a specific location, is just the sum of the vertical forces either on the left or on the right of this particular location where we want to find the shear force with uh, with the sign convention that all upward forces will be positive. And take note, if we will use the right segment, say for example this, we must multiply the summation of the forces to the right of this particular location that we want to find the shear force. We have to multiply that summation to -1 to give the same magnitude of shear force that you will get if you will use the left segment of the beam. And we formulate as well the A formula for finding the bending moment at any particular location. And it states that the bending moment at any particular location is just equal to the summation of the moment about that particular location of either the forces you will see on the left segment or the left of that particular location or to the right of that particular location. With the sign convention of this, if we will use the left segment, we have to assign positive senses to all the clockwise moments, but opposite of that if we will use the right segment. So those are what we have studied on our previous discussion. And if you can recall as well, we have known from the previous discussion that we can express the shear and bending moment acting at any particular point along the beam using uh, the it a function which is a function of the distance of that particular location with respect to a certain reference line. We usually uh, use the left segment, or I mean the left end. We usually use that left end as a reference to our distance x. So we have studied from the previous discussion how to get that particular uh, shear force at any distance along the beam with respect to with respect to its distance from a certain reference point, usually the left end, and as well as the bending moment. So we express the shear and bending moment in terms of its location with respect to the left end. So that is what we have learned, and that is what another thing that we have learned from the previous meeting. And last thing that we have learned from the previous meeting is how the beam actually behave if it experience a positive shear, positive bending moment, and positive normal force. So to show how the beam will behave when acted upon by these positive internal forces, let's try to observe what will happen on this particular section of the beam. So I just redraw the connection of the beam. Say, for example, this section is this particular section. So let's see how the beam will behave when acted upon by what we call positive shear force. So the beam will behave in this manner. So as you can see, the left segment or the left portion moves or shear off upward while the other segment moves on the opposite direction. So this is how a positive shear force affect the beam. It tends to shear off the beam in a manner that the left segment will move upward and the right segment will move downward. Or you can take this positive, you can take the effect of this positive shear force as it tends to produce clockwise moments on both of the segments of the beam. So that is how a positive shear force affects the beam. How about the bending moment? So from the previous meeting, we have learned that a positive bending moment tends to bend the beam in such a way that it will concave upward. So like this. And last thing that we have learned from the previous discussion is the effect of a positive normal force in a beam. So a positive normal force tends to elongate the beam like this way. So we can actually use this method, the method of sections, if you want to find the internal forces, the shear force, normal force, and bending moment acting along the beam at any particular point. We can use this technique or we can use this method if you want to. But in real life, guys, as a civil engineer, every time we design a structure, say for example, a beam, uh, we are not actually concerned on all of the shear and moment as well as the normal force acting along the beam. We are not always concerned to any other internal force acting on the beam other than the maximum values of the shear and moment or bending moment acting on the beam. So that is what we are usually concerned every time we design a structure as civil engineers. We usually are concerned with the magnitude and the effect of the maximum value of the shear force and bending moment that the beam or the structure will experience when loaded upon by certain type of loading. And we know for a fact that the values of this shear force and bending moment are usually vary with respect uh, to the length of the beam. We know for a fact that the normal force usually don't or doesn't vary along the length of the beam. Usually it's constant along the length of the beam. But the magnitude of the shear force and bending moment, as we have seen before on our previous discussion, we have seen that their values vary with respect to the distance, with respect to any other reference line. And again, usually that reference line is the left end of the beam. So since it varies, it will have different magnitudes. And again, like just like what I've said before, we are concerned on the maximum value that the beam will experience, the maximum value of shear force and bending moment that the beam will experience. And one great way or one technique that we can use to be able to easily find that maximum value of the shear force and bending moment acting on the beam is by drawing what we call shear and bending moment diagrams. So actually, for this meeting, that is our goal. So in order for us to provide that diagram, we first need to know the relationship between the load, the shear force, and bending moment diagram. So we need to know first what are the relationship between the load diagram, the shear force diagram, and the bending moment diagram in order for us to derive a technique or a particular procedure on how to draw the shear force and bending moment diagram. Because if we will not study the relationship between this load, shear force, and bending moment diagrams, we cannot provide a, a what we call a technique or a very easy procedure in order for us to draw the shear force and bending moment diagrams that are being experienced by our structure, say for example, a beam. So that's our first goal for this discussion. Our next goal is to establish, that's our main goal for this discussion. That's why we study first the relationship between the load, shear force, and bending moment diagrams. Our main goal for this discussion is to establish a procedure on how to make the shear force and bending moment diagrams for any particular beam that is loaded by any particular type of loading or the combination of these types of loadings. So these are our goal for this discussion. But in order for our discussion to be effective, actually I have prepared something for you so you can check your canvas after this discussion because I have prepared a very short sheet work for you. So the deadline of that sheet work is until 11:30 a.m. only. So that is the end of our class for this meeting today. So that sheet work, I gave that sheet work on you just to test if you really understood the topic that we have studied today. And for you to be able to practice solving problems related to our topic for today, I have prepared another thing for you. So I have prepared an assignment. Actually, it's a set of problems that I want you to solve for you to practice solving problems related to our topic, which is shear and moment diagrams on beams. So the deadline for that problem set for that assignment is on June 20 until before midnight. So you can access this sheet work and assignment on Canvas on the assignments tab. So just check them out after this lecture. So now let's move on to address our first goal, which is to understand the relationship between the load, shear force, and bending moment diagrams. So to demonstrate or to explain the relationship between the load diagram, the shear force diagram, and bending moment diagram, say for example, I have here a beam that is simply supported. So we know for a fact that simply supported beams have one hinge and one roller support. So a total of three reactions being exerted on the beam. And say for example, the beam is loaded by a certain type of load, W, and let's just assume that for generality, the load W is a function of x raised to a certain degree. And say for example, we already know we know the shear and bending moment that is acting along the beam as a function of x, which is the distance of the particular location where we are interested to find the shear and moment, shear and bending moment, and x is with respect to usually the left end of the beam. So for example, we have this. We already established these equations that shows the magnitudes of the shear force and bending moment acting along the beam with respect to the left end. So usually what we will have here are equations. And since these are equations, we can graph this. Actually, the graph of this two is are what we call the shear force diagram and bending moment diagram. But actually, the method to derive that particular graph is somehow tedious in a sense because we have to establish first these equations. And actually, these equations are only applicable for a particular type of load. So, what if the case is the beam is loaded by different types of loads, a combination of the different types of loads? So, we can use other method which is the singularity equation, but to derive a very simple technique on drawing the shear and moment, bending moment diagram, we will just study the relationship between this load, the load applied to the beam, the relationship of this load to the shear diagram, and the bending moment diagram. So to explain the relationship, let's focus on the beam. We know for a fact that the beam is composed of infinitely many particles like this. So we just simplified the particles composing the whole beam by this figure. We know for a fact that the beam is composed by this infinitely many particles. But just to simplify things, let us just assume that the beam is composed of this differential uh, volume. It's like a cube with a length equal to, let's say for example, let's name the differential length, the length of a differential area. Let's call that dx. We usually indicate dx as a very small length, infinitely small length. So now let's observe what are the internal forces being experienced by this particular differential area, for example, that is composing the whole beam. So in order for us to investigate the internal forces acting on this differential area, we have to separate it from the whole beam. So we need to cut it and put it here. So let's draw the free body diagram of this differential area. So we know that every time we draw free body diagram, we just put the external forces acting on the body. So what are the external forces acting on the body? So first thing is the load applied to the beam, but it only carries the portion of the load from this point to this point. So let's call that again W. And what else? What are the other things? What are the other forces acting on this body? Obviously, the internal forces acting on this side and this side. And actually, those internal forces are what we call shear force and bending moment, like this. So let's just assume the positive senses of the shear force and bending moment acting on this face. So this is the positive senses of the shear force and bending moment acting on this face. And like what I have said before, the shear and bending moment varies along the length of the beam. So meaning the magnitude of the shear and bending moment at this point is different on this point. So for simplicity, we will just designate the difference between the shear force and bending moment at this location and this location as differential shear force or differential moment, dm and dv. So if the change in shear force on this very small length is dv, for example, therefore the shear force acting on this particular side of the beam will be v plus the change in shear force, which is dv. And in the same manner, the bending moment acting on this side of the beam will be m plus the change in moment, which is dm. So these are the external forces acting on this part of the beam. And take note, these green colored forces and moments are actually external with respect to this body, because these are forces or internal forces exerted on this body by the adjacent bodies. So technically, these are external with respect to this body. And if we will recall, if the whole beam is in equilibrium, therefore, all of its parts must be also in equilibrium, meaning this free body diagram must be also in equilibrium, meaning if we sum up forces along the horizontal, vertical, and moment, all of these values must be equal to 0. So let's apply these three equations of equilibrium to this body. So let's start with the summation of forces along the vertical direction. So let's sum up the forces along the vertical direction. And what are those? With the sign convention upward positive. What are those vertical forces? First is V, and it acts upward, so its sign is positive. Next is this somehow different magnitude of shear. So it acts downward, so let's have a negative sign. assigned on it because we said that upward forces are positive. What else? The resultant of this uniformly distributed load, which is just equal to the area of this load diagram with a dimension of dx by w. And it points obviously downward, so its sign must be negative. So there are no more other vertical forces acting on this body. So according to this equation, the sum of these vertical forces must be equal to 0. So if we simplify this equation, we can see that the v will cancel out because it will be v minus v. The negative will be put here, so it will be negative dv. And if we put negative w dx to the right side as well as the negative, and then divide the equation by dx, we will have this equation. So what does this mean? So take note, V corresponds to an equation which corresponds to a graph according to this equation. And we know that dV over dx is the slope of the shear diagram or the graph of the shear equation we have here. And according to what we have here, the slope of the shear diagram at a certain point is equal to the magnitude of the load acting on the beam which corresponds to the graph of this shear diagram. Or in formal description, according to this equation, we can say that the slope of the shear diagram between any 2 points, say for example this point and this point, between any 2 points on the beam is equal to the applied load by that bounded by these points, meaning the slope of the shear diagram between this point and this point, which is this, is just equal to the magnitude of the applied load between these 2 points, which is W that points downward, so it must have a negative sign. So that is one of the relationship that we can establish between the load diagram and the shear diagram. And if we simplify this differential equation, if we solve this differential equation, cross multiply, put dx on the right side of the equation, and then integrate with proper limits. Since we have dv on the left side, so the limits must be in terms of shear force, which is from this shear force to this shear force, which is this. On the right side, we have dx, so the limits must be in terms of x. And what is that x? The distance of the particular differential area we are concerned, which is this, with respect to a reference point, which is, we assume, the left end. So that is x, and the location of the other point is at a distance the larger of differential x. So the total distance will be x plus dx. So that will be the limits for this integral. So simplifying the left side, we can easily simplify this integral. Integral of dv is just v. Substituting the limits, we will have a result of dv. And actually, if you can notice, this right side of the equation corresponds to the area of the load diagram. Like, because uh, we know for a fact that the area of the load diagram is just the product of the magnitude of the load diagram and the span that it acts, which is this. And since we are integrating, meaning we are summing up all of this area of the load diagram from x, from a certain reference point to another reference point. So what does this mean? what does this equation mean? It just shows us that the change in shear, which is this means change in shear, right? It tells us that the change in shear between any 2 points on the beam, so for example, the change in shear between this point and this point, is just equal to the area under the load diagram bounded by this point, which is this. So actually, that is a very helpful information that we can use to draw the shear force diagram. So later on, when we solve a problem, we will apply this information that we have derived in this scenario. So this is just for the shear force. Now let's go on with using the other equation of equilibrium, which is summation of moment must be equal to 0. So let's take moments at the left point dito on this point, assuming that clockwise moments are positive. So according to the equation of equilibrium, the summation of moments about this left end must be equal to 0. So let us just sum up all of the moments and forces that we see about this left end. So let's start with this couple moment. So according to statics, the moment of a couple moment at any point along its plane is just equal to its magnitude, meaning the moment of this couple moment about this point is just equal to m. So it points clockwise, so it must have a positive sign. Next is this couple moment. So again, like what I've said before, the moment of this couple moment about this left end is it just equal to its magnitude. But since it points on the counterclockwise direction, it must have a negative sign. Next is we have to moment this shear force acting downward with respect to this left end. So this is the magnitude of that force, because since moment is just equal to force times perpendicular distance, which is dx, we just have to multiply this shear force by its perpendicular distance, which is dx. But take note, the direction of the moment of that shear force is acting clockwise, so it must have a positive sign. Lastly, we have to get the moment of this distributed load about this left end. So we just have to first solve for the resultant, which is just WDX, and then multiply it by the moment arm, which is just half the length. So we just have to multiply it by the half of dx. So according to this equation, the sum of these moments must be equal to 0. And so solving and simplifying this equation, we can see that m will be cancelled because m minus m is just equal to 0. So negative dm will retain as well as vdx. But if you can notice, we will have a term which is a product of dx and dv, as well as a product of dx and another very small distance dx. You have to realize that when you multiply uh, two very small magnitudes like this one, we dx tells us that its length is very small. Every time we see d, which denotes differential, it denotes a very small quantity. So this dx denotes a very small quantity x, and this dv denotes a very small quantity v, which is the shear force. And if these two are very small quantities like this one, if we multiply a very small quantity to another very small quantity, if you can notice, their product is actually approaching 0. Like for example, if you will multiply 0.01 by 0.02, you can see that their product is actually less than zero point zero 0.01 as well as less than zero point zero 0.02. So so every time you multiply a very small quantity by another very small quantity, the product just approaches zero. So we can assume that the product of dx and dv is just equal to zero, as well as the product of dx and dx. So these terms are just cancelled. So the remaining terms are negative dm and vdx. If we put negative m to the right side of the equation and then divide the whole equation by dx, we can see that the result will be this. And again, take note, m corresponds to a graph of a certain function. So what does dm over dx means? It just means slope. Slope of what? Slope of the moment diagram. And according to this equation, the slope of the moment diagram is just equal to the magnitude of shear force, or in terms of formal definition, we can say that the slope of the moment diagram, which is this, between any 2 points, say for example this point and this point, on the beam is equal to the shear force bounded by these points. So if we will just look on the corresponding shear force acting on this point and this point, the magnitude of that particular shear force is just equal to the slope of the moment diagram. So that's another relationship between uh, load diagram, shear force diagram, and bending moment diagram. Actually, the relationship only on shear force and bending moment diagram. So using that relationship, solving this differential equation, multiplying the right side by dx, and then integrating with the limits of, since the left hand side of the equation has dm, so the limits must be in terms of m, the moment, bending moment at this location, which is this, bending moment at this location, which is this, and the right side has a limits of dx, so the limits must be in terms of distances. And if we simplify the left portion of the equation, we can easily see that the simplification of this integral is just equal to dm. So that dm is just equal to this. And what does that mean? It just shows that the change in moment, dm corresponds to change in moment between this point and this point. It just shows that the change in moment, which is this, between any 2 points on the beam is equal to the area under the shear diagram bounded by these points. Because if you can notice, this is just the area under the shear force diagram between this point and this point. So that is another useful information that we have derived from this derivation. So these two statements are the information that we will use in order for us to provide a technique, a simple procedure on how to draw shear force and bending moment diagram. And if you can notice, the 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 degree of the curve, or of the equation increases as you go from the load diagram to shear diagram to moment diagram, because we know for a fact that every time we integrate, so w is equal to kx to the n, x to the n. We know for a fact that every time we integrate, we add 1 to the exponent of the independent variable. So obviously, the equation that we will get here is 1 degree higher than the load diagram. The equation that we will get on the shear diagram will be 1 degree higher than the load diagram, as well as this. The degree of this moment diagram will be 2 degrees higher than this, because we will use shear force, the shear force equation here, which is again 1 degree higher already than the load diagram. And then we will integrate it again, so we will add another 1 on the exponent, so it will be 2 degrees higher than the load diagram, or 1 degree higher than the shear diagram. So we have to uh, note that, because again, that is another useful information that we can use in order for us to easily draw the shear force and bending moment diagram. So to better understand what I have discussed here, what I have derived here, let's apply these things in a sample problem. So as you can see, we are uh, referring to some kind of areas here. So actually we can use integration to find these areas that we have shown here, but a very easy way is just to memorize the formula on how to find the areas of certain common shapes, because usually the shapes of the loads being experienced by a structure, say for example a beam, can be represented by these common shapes. So if we know how to find the particular formula for the area of this particular common shape, we don't have to use integration anymore. We can just memorize this, the formulas for on how to find the area. For example, the area of a circle, or the area of a rectangle, a triangle, or a spandrel. If we memorize the formula on how to find the corresponding areas under these common shapes, or inside these common shapes, we don't need anymore to integrate. So we can use this as a supplement on drawing the shear force and bending moment diagram. So you have to memorize this. You have to be familiar with the different formulas of the different common shapes, which are again the usual shape of the load diagram, which the beam usually carries or supports. So now, let's proceed on uh, applying what we have learned, or applying the information that we have derived previously on this simple sample problem. So there is this is actually an overhang beam. It's not a simply supported beam, because you have a little overhang here. So this is called overhang beam. So we have an overhang beam, and the question requires us to draw the shear force and bending moment diagrams, as well as it requires us to determine the maximum moment M, the maximum bending moment being experienced by the beam, as well as its location from the left end. So we have a reference point, which is the left end. Actually, again, like what I have said before on my introduction, the main advantage of drawing the shear and moment diagram is that we can easily locate the location of the maximum values of the shear forces and bending moments that being experienced by the beam, as well as its or their actual magnitudes. So, in order for us to draw the shear and bending moment diagram of the sample problem, we will now establish a very easy procedure to follow on drawing shear force and bending moment diagrams. So, first of the simple procedure, obviously, is actually before you find the reaction, you have to draw the free body diagram of the beam first. So, assuming that we already know the free body diagram acting on the beam, since we have a hinge support here, we know for a fact that The external forces exerted by a hinge to the beam are two forces. Let's just call the vertical force, since this is hinge and along the vertical, along the vertical. Let's just call this force HB. I will not draw anymore the horizontal component of the hinge reaction because we know that that horizontal force is equal to 0 because there is no horizontal force acting on the beam. I will just call the reaction on the roller as RV. So roller reaction along the vertical direction. So how can we solve this? How can we solve the reactions? So very simple. We just apply statics. The equations of equilibrium, summation forces horizontal, vertical, and moment must be equal to 0. So let's start with summation of moment. So let's just try to find the summation of moment at point H, taking counterclockwise moments as positive. So we start with RV. So moment is just equal to force times perpendicular distance. So this is the force RV, and the perpendicular distance with respect to point H is equal to 2 plus 2 plus 1, which is equal to 5. And its direction is counterclockwise, so it must have a positive sign. Next, we will take the moment of this triangular load with with respect to this left end. So the area of this triangular load corresponds to its resultant. So the area of a rectangle of a triangle is just equal to 1/2 base times its height. And the moment arm, according to uh, the figures, the common shapes that I have presented before, the location of that resultant is just two-thirds of the base. And again, the direction of that moment is clockwise, so it must have a negative sign. And then take the moment of this rectangular load about point H, so that the moment is just equal to the area of this rectangular load, which is just equal to base times height times the moment arm, which is half of this plus this, so 2 plus 1. And last, we have to take the moment of the concentrated load acting on the overhang part, the right end. So the moment arm is the same as this. No, there is a 1 meter gap. So the moment arm will be 1 plus 1 plus 2 plus 2, a total of 6. So its moment is clockwise. So it must have a negative sign. So according to this equation, the summation must be equal to 0. So solving for RV is just equal to 3.27 kilonewton. It is positive, so meaning our assumed direction is correct. So it acts upward. Next, to find HB, we can use this equation of equilibrium. Summation of forces along the vertical direction must be equal to 0, upward positive. So the vertical forces acting on the beam are HB, RV, 1.5, and this triangular and rectangular load. So let's just sum up their magnitudes and take note that we already solved for the value of RB, which is 3.27 kilonewton. So we just have to substitute that here to solve for HP, which is this. So again, it has a positive sense or positive value. So meaning our assumed direction is correct. So let's put those correct magnitudes. So that is the first step on our procedure. The second step is we have to establish the critical points on the beam. So what are the critical points? Obviously, these are points, but how can we say that a particular point is a critical one? So usually, we take these things that I will enumerate, we take this as critical points. First is the location of support. So the locations of support, we can denote those as a critical point. Another thing that can be uh, assumed a critical point is the location of internal hinge or internal roller if there is any. And according to our figure, there is no internal hinge nor internal roller. Another point that we can assume as critical is the location of change of loading. So the interface of any different loading can be assumed critical. So say for example, this triangular load and this rectangular load, their interface is this location or this point. So we can assume that this point is a critical point. Lastly, we can assume, or second to the last, we can assume that the location of zero shear is also a critical point. Although in this diagram, we can establish already the point of zero shear because we don't have any shear diagram in the first place. So later on, we can establish the location of zero shear as we go on with our procedure. And lastly, the location of zero bending moment can be assumed as a critical point. And then again, we can establish that point at this moment because we neither have the shear diagram nor the bending moment diagram. So if we will try to apply these things that I have said here on this beam, we can see that this point is a critical point because it is a location of support. And this point is a critical point because it is a location of change of loading. This point is also a critical point because it is a location of change of loading as well. We have a rectangular load on the left of this point, but on the right, there will be no load. So there is a change in loading at this particular point. So that is a critical point according to these things that I have said. This point is again a critical point because it is a location of support. And this point is another critical point because it is a location of change of loading. On this part, we don't have a load, but on this part, over this point, there is an added load 1.5 kilonewton concentrated force. So that is the second step. Third step of our procedure to draw the shear force and bending moment diagram is we have to plot the corresponding shear force acting at any one extreme end of the beam. So meaning you can choose if whether you will use the leftmost end or the rightmost end. But on this procedure that I will explain, we usually use the left end as the extreme end. So how can we plot the shear force acting on this extreme end, on the left end? You have to have first a coordinate system, of course, because you are plotting it. So let's just take this horizontal axis as x, which corresponds to the different locations of different points along the beam. And let's take this vertical axis as the magnitude of the corresponding shear force acting on the different points along the beam. So how can we plot the shear force at this extreme end? You have to remember that the shear force at an extreme end, which is this, is equal to the concentrated force acting over it. So can you see any concentrated force acting on this end or point? We can see that there is a concentrated force 1.23 kilonewton acting on this point that came from the hinge support. So according to this statement, the shear force acting on that left end or extreme end is just equal to that um, concentrated force, the magnitude of that concentrated force. But you have to take note that we have sign convention because we are plotting it. So how can we know if we will plot above the 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 horizontal axis or below the horizontal axis? So our sign convention that we can use on this technique that we are establishing is that all of the upward concentrated forces will be marked as positive. Otherwise, it will be marked as negative. So since this is upward force, we can say that it is a positive concentrated force. So the shear force that results from this concentrated force will be also positive with a magnitude same to this magnitude, which is 1.23. So since it is positive, if we plot that on this diagram, which is actually the shear diagram, we are establishing the shear diagram on this moment. If we plot this, the shear force acting on this point, on this shear diagram, since it is positive, we must locate it above the horizontal axis. So let's assume let's let's assume that the this is the magnitude of the magnitude of the shear force acting on the left end, which has a magnitude of again 1.3, the same on the magnitude of the concentrated force acting on the extreme end. So that is actually the third step. The next step, the fourth step, for us to be able to draw the shear moment diagram is that we have to compute and plot the shear forces acting on the other critical points because we already established the shear force acting on this critical point, which is the leftmost end. So the next step will be we have to compute for the shear forces acting on the other critical points. And after knowing the magnitude of those shear forces, we have to plot them on our shear diagram or shear coordinate system. But the question will be, how can we get the corresponding shear force at this location, at this location, at this location, at this location? This is when we can use the information that we have derived earlier. So I will just put some designation in these critical points. Let us just name this particular critical point, point 1, and then this point 2, point 3, point 4, point 5. And according to the information we have derived earlier, which is this, we have found out that the change in shear between any 2 points on the beam, which is this, is just equal to the area under the load diagram bounded by these points. So change in shear can be interpreted as a difference in shears. This is also equal to this. So let's just cite a specific example. Say for example, the shear force acting on critical point 2, which is this. Say for example, the shear force acting on this and is let's say for example, the shear force acting on this is subtracted from the shear force acting on this critical point, which is this. And according to this statement, that difference, which is this, is just equal to the area under the load diagram between point 1 and point 2, which is this. Meaning, if the difference between the shear force on this critical point and this critical point is just equal to the area of this load diagram bounded by point 2 and point 1. So after rearranging this equation, putting negative V1 on the right side of the equation to have an equation directly computing the shear force on point 2, we will have this equation. And since we already know the shear force acting on point 1, which is this 1.3, we can already substitute that on this equation. How about this one? How can we get the area under the load diagram between point 1 and point 2, which is this? Obviously, this is just a rectangular load. So the area of a rectangular load is just 1/2 base times height. Base times height. 1/2 of 2 times 1 kilonewton per meter. So we just have to substitute that on this equation. And it will give us a result of 0.23. Take note of the sign of the 1 kilonewton force because it points downward. So the result will be 0.23. So what does this mean? It just shows us that the shear force at point 2, which is this, has a magnitude of 0.23. So if we will plot that here, since it is positive, it must be above the horizontal axis. So let's just say this is the 0.23 shear force acting on point 2. Next, so we already established the shear force acting on point 2. Let's establish the shear force acting on point 3. So again, using the same analogy, which is this, we can say that the shear force acting on point 3 is just equal to the shear force acting on point 2 plus the area under the load diagram between point 2 and point 3, which is this, which is just a rectangular load. So since we already found the value of V2, which is 0.23, we can just add that to the area under the shear diagram, load diagram between point 2 and point 3, which is just a rectangle which has an area base times height. So substituting those here, we will have a result of negative 1.77. So always take note of the sign of the load diagram. Since it is pointing downward, it must have a sign of negative. So what does this mean again? This just means that the shear force acting on point 3 is just equal to negative 1.77. So the shear force acting at this point is just equal to negative 1.77. Negative, so if we plot that here, it must be located below the horizontal axis, just like how we plot points on a Cartesian coordinate system. So it has a magnitude of negative 1.77. So following the same procedure, we can compute for the shear force acting on point 4 using this similar formula. We can see that the shear force at point 4 is just equal to the sum of the shear force at point 3 and the area of the load diagram between point 3 and point 4, which is this. And you can see that there is no load between point 3 and point 4. So what does that mean? It just means that there is no area to be added to shear 3, which is negative 1.77. Therefore, shear force is just equal again to negative 1.77. So lastly, no, before we proceed, uh, take note of this concentrated load acting on point 4. You have to consider that when you draw the shear diagram. So you have to take note that when there is a concentrated force acting at a point, which is like this, 3.27 kilonewton due to the roller support, add it on the shear force acting at that point, which is this, to get the shear force immediately to the right of that point. So if we want to find the shear force immediately to the right of point 4, we just have to add negative 1.77 and 3.27, which will have a total of 1.50. So this 1.50 is actually the shear force immediately to the right of point 4. So if we'll continue to find the other shear forces, say for example at point 5 using the same formula, we can see that the shear force at point 5, which is this, is just equal to the shear force at point 4, which is this, which is 1.5, plus the area under the load diagram, which is between point 0.4 and point 0.5, which is obviously again equal to 0 because there is no load to begin with. So substituting those values on this equation, we can see that the shear force acting on point 0.5 is just equal to 1.50 positive. So it must be above the horizontal axis. But then again, according to this statement, there is again another concentrated force acting at point 0.5. So we just have to add that to the shear force acting on that particular or the same location. So this is positive 1.5 and this is negative 1.5 because it points downward. So the sum is equal to 0. Actually, that is how you will check if your shear force diagram is correct or not. The magnitude or the value that you will have on the other end of the beam must be always equal to 0. So if the magnitude of the sum of the shear force and the concentrated load acting on the rightmost end is equal to 0, therefore you can be assured that your shear force diagram is actually correct. So that is just step number 4. So the next step is, after we have computed the shear forces on these critical points and we already graphed them, what what we have to do next, according to procedure number 5, is connect these points acting along the shear diagram. But we don't just connect them using a straight line or whatever line we think of. We must connect them properly using the degree of the curve that must be present on the shear force diagram. And we know before, like what I have derived before, what I have said before, we know that the degree of the diagrams, starting from the load diagram to the shear force diagram to the moment diagram, increases by 1. So meaning, if you want to connect this point to this point, the degree of the curve that must connect these 2 points must be 1 degree higher than the degree of the load diagram between these 2 points. And according to this diagram, which is a triangular load, which has obviously a degree of 1. So if the degree of this load diagram is 1, therefore, the degree of the curve that connects these 2 points must be 1 degree higher, which is second degree. And if you can remember, second degree equations are actually parabola. But if you can remember as well, there are certain types of parabola. We have a parabola that concaves upward or downward. So the question will be, how can we connect these 2 points using a parabola? Do we need to connect them in this manner, concave downward? Or we need to connect them using this manner, which is concave upward? So how can we know? How can we know which is which? So in order for you to properly assess what type of curve you will use that 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 will connect the points that you plotted on the shear force diagram, I will put some table here which has the corresponding degree and the corresponding graph for that particular degree. So say for example, we have no degree. So 0 degree is different from no degree because 0 degree actually have a degree which is obviously 0. But uh, a graph can have a or a graph can also have no degree. And usually the graph that has no degree are actually points, just like that. So points, the graph of points actually have no degree. So next, The 1 degree higher from no degree is actually the 0 degree. Actually, what I will show here are uh, the, the consecutive degrees of certain graphs. So the 1 degree higher from no degree is actually a 0 degree. So from none, you will have a degree which is starting from 0. So what does a 0 degree curve looks like? It just looks like a horizontal line. So just like this one. This is just a horizontal line. So therefore, its degree is 0. Uh, the next degree, 1 degree higher from 0 is obviously 1 degree or first degree. So what does first degree curve looks like? So I already mentioned it here. It just looks like a straight line, but a diagonal line or an inclined line. So an inclined line is different from a horizontal line. An inclined line has a degree of 1, but a horizontal line has a degree of 0. So they are much look like similar, but they are actually different. So next, 1 degree higher on one degree is actually second degree. So actually the graph of second degree curve and up with respect to the shear force and bending moment diagram that we will use are actually almost the same. So they look like this line. So this is the curve for a second degree or third or fourth or any degree higher than 0. This line, this black line. But actually, like what I was said before, second degree curves or third degree or any other degree higher degree can look like this or this one. This one is concave downward. This one is concave upward. Actually, it can also have this kind of curve, concave downward, but the points that it connects will be coming from a higher point to a lower point. And we can have lastly this type of uh, graph, second degree or any other higher degree curve that connects 2 points coming from a higher point to a lower point. So if we want to connect this point to this point, which is a second degree curve, which of these four graphs will we use? So we are connecting a higher point to a lower point. So the graphs that connects a higher point to a lower point is actually this higher point to lower point and this. So now the question will be which of these two are we going to use to connect these 2 points? The point on point 1 and the point corresponding to point 2 on the shear force diagram. Which of these two? So to answer that is uh, we can use the spandrel image that is being produced on these figures. The blue shaded area is actually what we call spandrel, or not actually a spandrel, but it looks like a spandrel like this. This spandrel has a height on this side. So actually the red lines you can see here are actually the height of the corresponding spandrel image that is being produced on this corresponding curves. So now we can use that spandrel image to know which one of these are we going to use for certain situations for connecting 2 points on different situations. So how can we use that? How can we use that spandrel and its height? So you just have to remember the height of the resulting spandrel when you use this type of curve, second degree curve and up. The height of the spandrel on this graph must be coinciding to the height of the graph above the shear force diagram, which is the load diagram. So if this is the load diagram, where is the height of this particular load diagram between point 1 and point 2? Actually, it is located here on the point 2. So how can that information help us to know which one of these two will we use to connect these 2 points? So you just have to look which of the 2 points will have the height of the spandrel on the right side, just like this one. The height of the graph is on the right side. So you have to choose a graph that has the height of the spandrel on the right side. And obviously between these two and these two, the graph that has the height of the spandrel on the right side is obviously this one. So this is the spandrel, this is the height, the red line. So meaning if we want to connect this point to this point, we have to connect them using this kind of curve. So it will look something like that. It will look concave downward because this is concave downward. So that is how you graph or how you connect points in a shear force diagram. So let's try to connect the other points. Let's connect this point to this point. So how can we know what is the image of the line that will connect this point and this point? How can we know which of this will we use to connect this point and this point? Again, we have to notice the degree of the load diagram above this span, which is this. And obviously, the degree of this curve is equal to 0 according to this table. A horizontal line has a degree of 0. So meaning the degree of curve must on this span below the 0 degree curve on the load diagram must have a degree of 1. So what does a 1 degree looks like? Again, it just looks like a straight line, which is actually a diagonal line. So actually, there are no complications when you are connecting 2 points using 1 degree below 1 degree or 0 degree because all you have to do is just connect them directly. So just like this one, you just have to connect them using a straight line. So you have no complications. We just have complications when we connect 2 points using second degree and up and up. So next, let's connect this point and this point. So again, how can we know the particular graph that connects these 2 points? We just have to look at the degree of the curve on the load diagram. And obviously, the degree of the curve between this span of the load diagram has a degree of none. It has no degree. So therefore, the degree of the shear force diagram below this must be one degree higher than no degree. And what is the 1 degree higher than no degree? It must have a 0 degree. And what does a 0 degree graph looks like? Again, it's just a horizontal line. Lastly, we just have to connect this point to this point. And again, we just have to look on the degree of the corresponding load diagram, which is obviously again has no degree. So meaning the degree of the curve connecting this point and this point must be 1 degree higher, which is what is 1 degree higher between or 1 degree higher on no degree? It must be 0 degree, and a 0 degree just looks like a horizontal line. So actually, this is what we call the shear force diagram. This just sometimes we just have to shade this portion, the area between these lines that we have connected and the horizontal axis. So the shear force diagram is actually this shear force diagram. So that is how you make a shear force diagram. Although that is not the last step for drawing the shear force diagram, because if you can notice this curve, this graph actually intersects the horizontal axis at this particular point. Actually, this particular point is what we call the location of zero shear. So that is our last step for drawing the shear force diagram. We have to find what is the location of that particular zero force shear. So how can we find that particular location? If you can notice, this is a straight line which cuts this horizontal axis. And because of that, there is an image of a triangle being produced on this portion and this portion. If we try to zoom them out or zoom them in, they look like this. And what are the dimensions of these two triangles? The height of this triangle is actually the magnitude of the shear force corresponding to this point, which is 0.23. And the height of this triangle corresponding to this triangle on this portion is equal to the shear force acting on this point, which is obviously 1.77. So I just disregarded the sign because we are just making the shear forces as the dimension of the triangles. So if we just let this dimension of the triangle to be said as length x, and notice that this whole span is actually 2 meters long. So if this whole span is 2 meters long, and if we say that this is x, then what is the length of this span, which is this? So obviously this will have a dimension of 2 minus x. So actually we have produced a similar triangles. So again, using basic mathematics, the knowledge of basic mathematics, uh, if we have similar triangles by ratio and proportion, the ratio of one side to the other side of the triangle must be equal to the ratio of one side to the other side of the other triangle. Or in equation form, we will have here, we will have this. And solving for x, you can just use your calculator, your shift solve function of your calculator to solve for x, and you will see that the value of x is equal to 0.23 meters. So meaning this zero this zero shear force is located 0.23 meters from this point, from point 2. Or if we will use the leftmost end as the reference, the location of the zero force shear force, the location of the zero shear force is located 2 plus 2 2 plus 0.23 meters, which is equal to 2.23 meters, to the right of this left end, which is 0.1. So that is the location of the zero shear force. So actually, that is the last step. That is the last step for drawing the shear force diagram. And if you can remember, what I said before on step number 2, which are the definition of critical points, I have said that the location of zero shear is actually a critical point. So we will add another line here to designate the location of this particular critical point. So I will just name that corresponding location of the beam as point number 6. So again, locations of zero shear force are actually critical points. So every time you already solve for the location of those points, those zero shear force points, you have to add them as a critical point on the graph of your shear and bending moment diagram. There is actually another point here that has a zero shear, which is this. Actually, not zero shear. it intersects the horizontal axis, but actually the shear force acting on point 4 is not actually zero, sorry. It just intersects the horizontal axis, but the actual location of zero shear force is actually this 2.23 meters from the left end. So that is the last step for how to draw the shear diagram. So again, the shear diagram is just this. That is the shear diagram. So what is the purpose of the shear diagram? You can easily see, first is you can easily see the variation of shear force along the length of the beam. So using the diagram, you can see that there is this kind of variation of shear force acting on the beam, which has a maximum value of 1.5. If you will just look on the ordinate of the graph, you can see that the point or the maximum ordinate that we have is actually 1.5, meaning the maximum shear force acting on the whole span of the beam is actually 1.5 kilonewton. And where exactly this maximum shear force acts? It acts all the way from 4.4 to zero point 0.5 according to this graph. It has a constant magnitude of 1.5 kilonewton force between zero point 0.4 and zero point 0.5. So those are one of the things that we can see on a shear force diagram. Another thing is, obviously we already indicated the location of the zero shear force. Actually, the importance of the location of the zero shear force is that the maximum bending moment acting on the whole beam is actually always located on the location where the shear force is equal to zero. So you can expect that if when we draw the bending moment diagram, you can expect that the maximum ordinate or the maximum bending moment will be located at this point, at point 6. Why? Because it has a magnitude of shear force equal to 0. So now let's proceed to the uh, bending moment diagram. So actually the procedure for drawing the bending moment diagram is actually just the same as drawing the shear force diagram. We just have to change the concentrated forces or the forces on the procedures of the shear force diagram into moments. So actually, if you can notice, this is just the first step on drawing the shear force diagram. We have to plot the bending moment acting at one end of the beam. Actually, the concentrated bending moment. We have to plot the concentrated bending moment acting on one end of the beam. And again, the end of the beam that we use is the leftmost end. So we just have to plot the bending moment, concentrated bending moment acting on point 1 on a coordinate plane which has a horizontal axis, which is again the location of all the particular points along the beam, and a y-axis or the vertical axis corresponding to uh, the bending moments acting on the different points on the beam. So again, uh, by definition, just like on the shear force diagram, the bending moment at an extreme end is equal to the concentrated moment acting over it. So actually, the bending moment at point 1, according to this definition, is just equal to the concentrated moment acting on point 1 along the actual beam. And if you can notice, there is actually no concentrated moment acting on point 1. Therefore, the bending moment at point 1 is just equal to 0. So we don't have anything to plot in the first place because according to this definition, the bending moment at point 1 is just equal to 0 because there is no concentrated moment acting on point 1. But if in the case that there is a concentrated moment acting on point 1, we just have to plot its magnitude on the bending moment diagram with the sign convention of clockwise moments are positive, otherwise negative. So if we have a clockwise concentrated moment acting on point 1, we have to plot it above the horizontal axis because it will have a sign of positive. So next step is again almost the same to the shear force diagram procedure. We just have to compute and plot the corresponding moments acting on the other critical points other than the leftmost end. So we just have to find the bending moment acting on point 2, point 6, point 3, point 4, point 5. And how can we compute for the bending moments on those other critical points acting on the beam? Actually, again, we can use the information that we have derived on the start of our lecture. We have we have known that the change in moment, which is this, between any 2 points on the beam is just equal to the area under the shear diagram bounded by these points. Or if we will just apply that particular information on this particular problem, we can see that the difference between the bending moment at point 2, so for example, we already know the bending moment at point 2, the difference on the magnitude of that bending moment acting on point 2 and subtracted on the magnitude of bending moment on point 1, which is this, according to this information, is just equal to the area under the shear force diagram between point 1 and point 2, which is this. So meaning, if we know the magnitude of the bending moment acting on point 2 and point 1, their difference is just equal to the area of this diagram under the shear force diagram between point 1 and point 2 only. So meaning, if we can establish this area below or under the shear force diagram between point 2 and point 1 and point 2, we can already get the difference between the bending moment on these 2 points. Or if we will rearrange this, we can see that the bending moment at point 2 is just equal to the bending moment. The bending moment at point 2 is just equal to the bending moment at point 1 plus the area under the shear force diagram between point 1 and point 2 only. So substituting the corresponding values, we already know the bending moment at point 1, which is actually 0. And we can compute for the area under the shear force diagram between point 1 and point 2 as a second degree curve. And we can actually simplify the area of this second degree curve if we will cut this whole area into corresponding rectangular and parabolic area. So the dimension of the rectangular area is this. This is the height, which is 0.3. This is the length, which is 2 meters. And then the height of the second degree curve, which is a parabola. The height will be this height, 1.23, minus this height, which is 0.23. So that is just equal to the difference of these 2 points, two shear forces, which is just equal to 1. And then the length of the parabola is just again 2 meters. So if you will look on the formulas that I have gave before, you can see that the area under a parabola, which is concave downward, is just equal to 2/3 times the product of the base and the height. So substituting those values, we can have this equation. So bending moment at point 1 is equal to 0. We already found out that before. And then the area under the parabola minus we already reduced or subtracted the rectangular area here. The area under the parabola is just equal to the 2/3 ng base, which is 2 meters, times the height, which is the difference between the shear forces between point 1 and point 2, plus the area of the rectangular portion, which has a dimension of 0.3 by 2 meters. So simplifying that, we can see that the bending moment at point 2 is just equal to positive 1.79. Positive meaning uh, if we will graph that, it will be located above the horizontal axis. So this is the 1.79 bending moment at point 2. Next, if we will try to find the bending moment at point 6, according to this equation, the bending moment at point 6, which is this, is just equal to the bending moment at point 2, which is 1.79, plus the area under the shear force diagram between point 2 and point 6, which is obviously this. And obviously, this is just a triangular area. And the area of the triangle is just 1/2 base times height, with a height of 0.23 and a base which is equal to 0.23. So the area of that shear force diagram between point 2 and point 6 is this, added to bending moment at point 2, which is 1.79 computed a while ago. Simplifying that equation, we will see that it has a sum of 1.82. So if we will plot that, that will be above the horizontal axis. So again, like what I've said before, you can notice that the maximum bending moment is located on the same location of the zero shear force. So they are on the same location as verified on this graph. So we will just continue on finding the other bending moments on the other critical points, point 3, point 4, point 5. Using the same analogy, we can compute for the bending moments at the other critical points, say for example point 3. So the bending moment at point 3 is just equal to the bending moment at point 6, which is 1.82, solved a while ago, plus the area under the shear force diagram, which is this, which is again a triangle with a dimension of 2 minus 0.23 by negative 1.77. 2 minus 0.23 is just equal to 1.77. Simplifying, we will see that the bending moment at point 3 is just equal to 0.25. So positive again, so that will be plotted above the horizontal axis. Furthermore, the bending moment at point 4 is just again the same analogy as this. Substituting corresponding values, we will see that the bending moment at point 4 is negative 1.52, meaning if we plot that, that must be below the horizontal axis because it is negative. Lastly, the bending moment at point 5, again, using the same analogy, will be equal to 0. And again, just like on the case of the shear force, that is one way to check if your bending moment diagram is correct or not. The bending moment acting on the other extreme end, must be equal to 0. So if you can notice, we don't have a perfect 0 value because that is just due to the rounding off of the values. So if you can notice, we rounded off many values here. That's why we end up having negative 0.02, which is actually can be approximated as 0. So we can still say that our bending moment diagram is correct because we have computed a 0 bending moment at the other extreme end. So in the case, just a note for you, in the case that there is a concentrated moment acting on the any other point on the beam, just like what we had done on the shear force diagram, you just have to add that magnitude on the bending moment at that particular point. Say for example, you have a concentrated bending moment here. To find the bending moment directly to the right of this point or this section, you just have to add this magnitude of bending moment to that magnitude of concentrated movement acting on point 4, so that you will find the bending moment at the immediately to the right of point 4. So Although we are blessed because in this example problem, we don't have any other concentrated moment. So next step, second to the last step, is after we have plotted the corresponding magnitudes of the bending moments on the different points on the beam, again, just like what we did on the shear force diagram, we just have to connect those corresponding points with using the correct graph with respect to the expected degree of the curve on the bending moment diagram. So again, just like what we did on the shear force diagram, the the degree of the curve connecting these 2 points on the bending moment diagram must be 1 degree higher as the degree of the curve connecting on the shear force diagram. So we can see that the degree of the curve on the shear force diagram between point 1 and point 2 is 2 degree, second degree. Therefore, the degree of the curve that must connect this point to this point on the bending moment diagram must be 1 degree higher or must be third degree. So again, what does a third degree looks like? So again, using the table that I have provided before and the technique on how to properly choose which of these four graphs we will use to connect this point and this point. We have we are connecting a lower point to a higher point. So which of these four we will use? Either this or this, because this graph connects a lower point to a higher point, as well as this graph, it connects a lower point to a higher point. So these are the only two choices we have. But to know which of these two are is actually what we will use to connect this point to this point, again, we will use the spandrel technique. So the blue shaded area is actually the spandrel, and the height of that spandrel must be collinear to the height of the graph above it, which is the shear force diagram. And where is the height of this shear force diagram between point 1 and point 2? The height of this diagram is actually located here on the left. So which of these two has a height of the spandrel located at the left? So obviously this. So therefore, if we connect this point and this point, we will connect them using this curve, concave downward, just like this. So next, we will connect this point to this point, and we know that the degree of the curve above it is 1 degree. Therefore, the degree of the curve that must connect this point to this point must be 1 degree higher or 2 degree. But again, which of these four we will use? So again, if you will see, or if you will look on the shear force diagram, the height of that graph is located here on the left end. And again, just like this one, it connects lower to higher point. So which of these 2 points we will use, which has the height of the spandrel on the left end? So obviously this one. So again, just like this one, we will connect these 2 points using the same image as this. So it will be concave downward as well. Next is let's connect this point to this point. This is first degree, so this must be again second degree. We are connecting lower point to a higher point to lower point. So either of these two, a higher point to lower point, higher point to lower point. But if you will look on the shear force diagram, the height of the graph is on the right, and which of these two has the height of the spandrel located to the right? Obviously this. So we will use this graph to connect these 2 points. So it will be concave downward. Next, this point and this point, let's connect this point and this point. The degree of this curve above it on the shear force diagram is 0. Therefore, the graph must be or must have a degree 1. And degree 1 is just a diagonal line. So we will just connect them using a straight line. Lastly, we will connect this point to this point. So if you can remember, we have a zero bending moment here. And how can we connect them? If this is 0 degree, that must be first degree. And again, first degree is just a diagonal line. So actually, our bending moment diagram is just this. That is just our bending moment diagram. So the last step in drawing the bending moment diagram is again the same on the last step on drawing the shear force diagram, which is to locate the zero bending moment, because if you can see, there is this point which has a zero bending moment. So how can we find that particular location? Same method of what we did on the shear force diagram. We will have two triangles there. We just zoom in them here. And again, the dimensions are this, which is 0.25, and this has a dimension of 1.52. And then if we let this distance to be, say for example, x, and if this whole distance is equivalent to 1 meter, therefore this distance is just equal to 1 meter minus this distance, which is x. So again, by ratio and proportion, this side over this side must be equal to the ratio of this side over this side. Solving for x, we have 0.14 meters. So therefore, the location of this zero bending moment is 0.14 meters from point 3. Or if we will use the leftmost end as the reference, this location of the zero bending moment is located 2 meters plus 2 meters plus 0.14. It is located 4.14 meters from the leftmost end. So there you go. This is the complete bending moment diagram. So actually, that point of zero bending moment is actually what we call point of inflection. And like what I've said before, with respect to the left end, it is located 4.14 meters from the left end. And just like what the question asks, it asks the maximum bending moment and its location. And we can easily locate that maximum bending moment using the graph. Uh, we just have to search for the point or location which have the largest ordinate, which is obviously this, which is located again 2.23 meters from the left end. And the magnitude of the bending moment at that particular location is 1.82. Therefore, the maximum bending moment acting on the whole beam loaded by these loadings is just 1.82 kilonewton meters, which is located again 2.23 meters from the left end. So that is the answer for the first question, or the question. The answer for the question. And sometimes we are concerned again for the location of the maximum shear force, and like what I have said before, by just observing the shear force diagram, we can easily see where is the location of the maximum shear force. So you just have to find the location of the maximum of the just have to find the location of the point which have a maximum ordinate, which is obviously this, which is an ordinate of 1.50, and then 1.50 is actually the maximum shear force acting on the whole beam. And obviously it acts 6 meters. 6 meters ba? 2 meters, 2 meters, plus 1, plus 1. Actually, it acts from 5 meters to 6 meters, or we can say that it acts 6 meters from the left end. So let's just go back to the bending moment diagram. What are the things that we can see on the bending moment diagram? First is the maximum bending moment and its location, obviously. And then the location of the zero bending moment. Actually, that location of zero bending moment, which is called point of inflection, that is the point where the elastic curve which is the actual deflection of the beam, changes uh, its bending from being concave upward, for example, to being concave downward. So later on your subject structural theory, you will learn more about that on the topic of deflection. So there you go. That is how you draw the shear and moment diagram using this simple technique or simple procedures. So there you go. We already accomplished our second goal, which is we already established a procedure on how to draw the shear force and bending moment diagram. So we already accomplished that goal. So just to summarize what we have studied today on this meeting, we have seen that the slope of the shear diagram between any 2 points on the beam is just equal to the applied load bounded by these 2 points. And then using that, we found the information that the change in shear between any 2 points on the beam is equal to the area under the load diagram bounded by these points. And using the uh, bending moment, we have seen that the slope of the bending moment diagram between any 2 points on the beam is equal to the shear force bounded by these points. And lastly, using that information, we have known that the change in moment between any 2 points on the beam is equal to the area under the shear diagram bounded by these points. And lastly, uh, we have learned from our discussion the procedure on drawing the shear force and bending moment diagram, the easy way. So it is composed of 10 steps. The first step is find the reaction acting on the structure, acting on the beam, and then establish the critical points on the beam, and then plot the shear force acting at one end of the beam. We usually use the left end, and then compute the corresponding shear forces on the other critical points, and then connect these points that you have plotted on the shear force diagram with the proper graph with respect to the degree of the curve. And then after that, find the location of zero shear force, because we already know that the location of zero shear force is where the maximum bending moment is located as well. And that's the end of the shear force diagram graphing. So this next step is actually how to graph the bending moment diagram. So just like the shear force diagram step, we just repeated it here, changing the shear force as bending moment. So step number 7 is plot the bending moment acting at one extreme end of the beam, and then compute the bending moments acting on the other critical points, and then connect the bending moments using the proper graph with respect to the degree, and then find the location of the zero bending moment, which is actually called the point of inflection. So for you to be able to practice solving, I have given set of problems here for you to practice solving. So all you have to do is draw the shear and moment diagram, and then specify the correct degree of the corresponding curves, and then the location of the shear force and the zero shear force and zero bending moment. So specify the location of those points, and then specify the magnitudes and locations of the maximum shear force and bending moment. So the answer on those problems are actually here, but this is not the graph of the shear force and bending moment diagram. So these are just actually the some of the things that being required by the question. So that's all for this meeting. Thank you for listening. If you have any questions, clarifications, or any other concern, please do not hesitate to contact me via. You can use the discussions tab on Canvas, or you can message me on Messenger, or you can email me at my email. Here's my email. And that's all, and have a good day.